This chapter introduces momentum as a fundamental quantity for analyzing motion, particularly during collisions and explosions. The core principle is that the total momentum of a system is conserved if no external force acts on it, providing a powerful tool for predicting outcomes after interactions. 1. Linear momentum definition. Momentum is the quantity of motion of a moving object. Formula: P equals mv concepts. Momentum is a vector quantity. A change in momentum can result from a change in the object's speed, its direction, or its mass. Real-life example: a heavy truck moving slowly and a small car moving fast can have the same momentum. For example, a 4,000 kilograms truck at 2 meters per second has the same momentum as a 1,000 kilograms car at 8 meters per second. This means stopping them would require the same impulse. 2. Impulse. Impulse is defined as the product of the force and the time interval over which it acts. It is equal to the change in momentum. Formula: impulse equals F net T equals P on a force time Ft graph. The area under the graph represents the impulse. Real-life example: catching a cricket ball. A fielder pulls his hands back while catching a fast-moving ball. By doing this, he increases the time t over which the ball's momentum is brought to zero. A longer time results in a smaller impact force F, saving his hands from injury. This is the principle behind airbags, cushioned shoes, and bending your knees when landing from a jump. 3. Law of conservation of momentum statement. In an isolated system, the total momentum before an interaction is equal to the total momentum after the interaction. Formula for two objects colliding in one dimension: m1u1 plus m2u2 equals m1v1 plus m2v2. Key concepts. This law is a direct consequence of Newton's third law. For momentum to be conserved, the system must be free from net external forces. Real-life example: recoil of a gun. Before firing, the total momentum is zero. When fired, the bullet gets forward momentum. By conservation of momentum, the gun recoils with equal momentum in the opposite direction. 4. Elastic and inelastic collisions. Collisions are classified based on whether kinetic energy is conserved. Elastic collision: both momentum and kinetic energy are conserved. This is an ideal scenario, approached in collisions like billiard balls. Inelastic collision: momentum is conserved, but kinetic energy is not. Some initial K is converted into other forms of energy. Most real-world collisions are inelastic. Perfectly inelastic collision: a special case where the two objects stick together after colliding. Maximum kinetic energy is lost. Formula: m1u1 plus m2u2 equals m1 plus m2v. Real-life example: elastic approx. Two snooker balls colliding. Inelastic: a car crashing into a tree. Perfectly inelastic: a bullet embedding itself in a wooden block. Then, let's do some exercises on linear momentum. Change in momentum and net force. Newton's second law. Law of conservation of momentum. Elastic and inelastic collisions. That's end of this chapter. Enjoy, and let's see in the next video.